Okay, for this problem, we're trying to this figure with we are given a sandy type soil, and we are given with the properties of soil, which is void ratio and specific gravity. Compute for the saturated unit weight of the sand, effective stress at point A, and effective stress at point B. So before we solve that, we have to compute first for the saturated unit weight. So for this one, we have our I, hydraulic gradient, which has H all over L. So from this figure, our H is equivalent to H1, which is 1.2, and our L, 2.5. So it gives us I as hydraulic gradient is 4.48. For the saturated unit 8, you have this equation. You substitute the specific gravity, void ratio, the unit weight of the water. So saturated unit weight is 21.078 kilonewton per cubic meter. Then for the effective stress at point A, so for this effective stress, we simply have from the equation I, which has H all over L. So we make use of I is equal to H2 all over L2. So we get the value here for our H of 2, which is equivalent to, so we are on point A. So for H of 2, that is equivalent to, we make use of our equation, I times L sub 2. Our I is equivalent to 0.48. So H2 is, our I now is 0.48 times 0.8. So which means that our H2 is, from the figure, our L sub 2 is 0.8. So from the surface towards point A, so L sub 2 is 0.8. So if we try to substitute, so our H2 is equivalent to 0.384 meters. So our Y sub 2, so that is equivalent to 0.6 plus 0.8 minus H of 2. And that is now equivalent to Y sub 2 is 1.0116 meters. Now for our total stress. For our total stress at point A, total stress at point A, that is L sub 2 times the unit weight of the sand, which is equivalent to 21.078 plus this height, which is 0.6 times the unit weight of the water. So we have the value for our total stress now, which is 22.74 kilopascal. For the water pressure at point A, so that will be equivalent to, so you simply have to get the value for the water pressure at point A. So 0.6 plus 0.8 minus H is small, so minus H of 2, since the point is connected to the standpipe. So times the unit weight of the water. So basically that is now equivalent to, we have here 9.967 kilopascal. And therefore, to get our effective stress, you simply have to subtract 22.74 minus 9.96, and we have now 12.78 kilopascal. And for letter C, for the effective stress at point B, so Y sub 1, the value for Y sub 1 here So that is the total stress at point B. So L1 times the saturated unit weight of the sand we have computed plus the height of that, which has the height of the water, 0.6 times the unit weight of the water, 9.81. That is the total stress. For the pore water pressure at point B, that will be equal to zero point 0.6 plus 2.5. That one is connected to the standpipe. So minus small h1, which has 1.2, times the unit weight of the water. So meaning to say the point water pressure at point B, 9.81 times 0.6 plus 2.5 minus small h1, which has 1.2. So that is now the pore water pressure. So that is equal to 18.63 kilopascal. So the total stress is 58.58 kilopascal. And therefore, the effective stress, so you subtract 58.58 minus 18.639, so that is 39.94 kilopascal. Now we move on to the effect of capillary rise to soil stress. Capillary rise demonstrated in the following illustration. So for the capillary rise in soil, so a sandy soil is placed in contact with water. After a certain period, water rises and the variation of the degree of saturation with the height of the soil column caused by the capillary rise approximately given in the figure. So this is the figure showing the capillary rise. We have a container that has a water and we have a tube with a soil inside. We place the tube on the container with the water. After a certain period of time, this water will rise, or it will move upward to the tube through the soil porous, or through the porous of the soil rather. So which means that we have now the capillary rise. So which means that capillary, in our previous discussion in fluid mechanics, you already encountered a capillary rise. However, capillary rise in soil is the same way, is somehow different here, which is this is the movement of the water upward due to the porous of soil. So this is the setup wherein we have as water, we have a container with a soil, then at a certain period of time, the water will move upward to the soil porous. So it moves because of the spaces between the soil. So it will rise into the container of the soil sample through the soil porous, or the particles, the void within the particles. So the height with the water rises dependent on the soil pores, or the void of the soil. So this is now the illustration. So we have with the capillary rise denoted by H of 1, and so that is now our capillary rise, which is our H of 1. So as the water move upward within the soil particles. The degree of saturation is about 100% up to height H of 1. Beyond the height H1, water can occupy only the smaller voids, hence the degree of saturation is less than 100%. So within this small h1, the degree of saturation is 100%. Beyond h1, the degree of saturation is less than 100%. The approximate height of capillary rise is given by the equation of Hazen formula. So that is the approximate height of the capillary rise, where our d sub 10, if the effective grain size, our E is the void ratio, and C is a constant that varies from 10 to 50 mm squared. So the pore water pressure at a point in the layer of soil fully saturated by capillary rise is given by this equation. Within the capillary rise, within the soil layer that is saturated by the capillary rise, so the pore water pressure is negative. The unit weight of the water times H, which is the height of the point under consideration, measured from the groundwater table. If a partial saturation is caused by capillary action, the pore water pressure can be approximated by this equation. So that is now negative degree of saturation times the unit weight of the water times H. So this is the partial saturation caused by capillary action. Our S is the degree of saturation, of course, and the point under consideration. So if we have the soil layer, so from this figure, from this illustration, for the capillaries, you have the water table. So we have here soil sample at a certain period of time. This water rises within the soil layer through the pores of soil. So that height on which the water rises is within the soil layer is called the capillary rise. So of course you have here, so you have illustration here. At a certain point, you have to compute for effective stresses, point A at point B at point C. So for this figure, if you're going to compute for the total stress at point A, so that will be equivalent to, so H1 times the unit weight of which is gamma 1 times this H of 2 from the ground surface towards point A, that is small h2, times the unit weight within the soil layer. So that is the total stress. So the pore water stress at point A, since point A is within the capillary rise, so meaning to say, class, that this is partial saturation at point A, has a partial saturation that is caused by capillary action. So our pore water pressure at point A will be equivalent to negative S times the unit weight of the water times our H of 3. So that is our H of 3. At point B, to compute the total stress will be equivalent to, at point B, small h times the unit weight of the of that soil layer times H1 times the unit weight of that soil layer. And the pore water pressure at point B will be equal to, point B is within the water table, so point B at pore water pressure is 0. So the stress at point C, the total stress will be equivalent to H4 times the unit weight within the soil layer plus small letter h times the unit weight within the soil layer plus times small h1 times the unit weight of the particular soil layer. The pore water pressure at point C now, since point C is below the water table, so which means H4 times the unit weight of the water, so that is the pore water pressure.